All right, finally we can get to the last portion of material that I wanted to cover this semester, and that deals with subatomic physics. We've been looking at nuclear physics so far, but we can break things down even farther than that, and we can go to the constituents of what are called hadrons, which are quarks. Okay, and so we thought before that our elementary particles were the proton, neutron, and electron, and that you couldn't get down any farther than that. Turns out that according to what we call the standard model, that's still true here. This is an elementary particle. And cannot be broken down any farther as far as we know right now. Now we should, put a big qualification on this. It could be that there are a whole infinite series of other smaller particles and other forces that we don't know about yet. That's still possible, but as far as we know, in terms of the basic forces of nature and what's called the standard model, the electron is an elementary particle. And it's called a fermion. And a fermion is a spin 1/2 particle, but it also has another name. It's called a lepton. A lepton is a very light particle. That is elementary. And in contrast, we go, what about the proton and the neutron? Well, the proton and the neutron are what are called baryons. And baryons are composed of even more elementary particles called quarks. And so this then deals with what's called the strong force. These baryons are held together essentially by the strong force. So these quarks then are in groups of 3. And these quarks have fractional electric charge. Okay, and there are several different types of quarks. If we look up at the data projector for a moment, we see that here is an up quark, and that up quark has a charge of 2/3 of an elementary charge on, say, a proton or an electron. And a down quark has a -1/3 elementary charge. And notice that there are some numbers that are associated with them. It's called baryon number. Okay, now, since they're not a full baryon by themselves, their baryon number is 1/3. And so what this means then is that when you put 3 of these together, you get a single baryon. And the simplest examples of baryons, as I mentioned before, are protons and neutrons. Now, they're up and down. There's also strange and charm, bottom and top. But in the first generation of quarks, these are the ones that I want to talk about first. Okay, so it turns out there are 3 generations of elementary particles. And the first generation are the most common ones that are lowest energy. Like, for example, the proton and the neutron. If we're talking about a first generation baryon. On the other hand, if we're talking about a first generation lepton, then we'd be talking about an electron. Or, as it turns out, we also have a neutrino here. It's also considered to be a very light particle, not zero mass, but very, very light, that is in this category of leptons. Okay, and so these first generation ones are most common, and the reason for that is that this is the lowest energy state that the matter can have. But there are two other generations of elementary particles too that are higher energy versions of the proton, neutron, electron, and neutrino. And we'll get to those later. But let's just focus in on the first generation particles, which are the most common and the ones that we'll be dealing with the most in this class. Okay, so if we're interested then in these quarks, the first generation quarks are the up quark, U, and the up quark has a charge of plus 2/3 times the elementary charge. Okay, and so the elementary charge E here is equal to 1.6 times 10 to the minus 19 coulombs. So we thought before that that's the small of a charge as you can get, but no, the quarks have fractional pieces of this elementary charge. Then we also have a down quark, D for down, and that is minus 1/3 of a elementary charge. And so if we are to get 3 of these together, that will form either a proton or a neutron, we have to conserve charge. And so there's certain things that we need to conserve in order to see what reactions are possible. Okay, so charge conservation just says that charge can't be created or destroyed. And so the net amount of charge in the system has to remain constant. Another constraint we have on what reactions are possible is that we have to have conservation of momentum and energy. Or if it's relativistic, you could say that the two together are conserved. You have conservation of mom energy, sometimes it's called, in a relativistic system. Another thing that we have to have is conservation of baryon number. Which just means that the total number of baryons before an interaction has to equal the total number of baryons after an interaction. And we also have to have conservation of lepton number. Now we'll talk a little more about how we assign these numbers to the baryons, which are like the proton and the neutron, and the leptons, which are like the electron and the neutrino, in a little while. But if we are to construct our first generation proton out of up and down quarks, these are our basic constituent first generation quarks, then what we're going to need to do for a proton is say, well, okay, I know that there's got to be 3, and I know that it's got to add up to +1 for the charge. This is conservation of charge. If I add together a bunch of these things, I know that the total is going to be the sum of the individual charges that make up the 3 quarks. Okay, so a proton then, P, can be thought of then as 2 up quarks and a down quark. And remember that here we've got +2/3 of an elementary charge, right? We're assuming here that we know that that means times the amount of charge in an elementary unit of charge. And 1 down, which is -1/3. So this gives us a total charge of +1. Similarly, for a neutron, we can say, well, that has 0 net charge. And if it's going to be made out of 3 of these first generation quarks, which are up and down quarks, then the only way we can do that with 3 of these is to have 1 up and 2 downs. Okay, and so that gives us a total charge then of 0. Now I should mention that we can also have anti-quarks. So it's not just the up and the down for first generation quarks, but also the anti-up and anti-down. Okay, so an anti-up quark would have a charge of, well, when you do the antiparticle, and here this is just the antiparticle of the up quark, okay, that's going to have a charge of -2/3 e, and the anti-down is going to have a charge of +1/3 e. Okay, so anytime you create quarks, you have to create a particle-antiparticle pair. Okay, and so this is important because if you don't do that, then you don't have conservation of charge. If you're to create matter out of energy, and energy doesn't have charge, that means that the particle and the antiparticle must have opposite charges so that you have the same amount of charge before as you did after. So that's the kind of thing that I'm talking about here when I say we have to conserve charge as well as these other principles. And that kind of puts a straitjacket on the kinds of nuclear reactions that are possible. Okay, so our proton then looks like this. Our neutron looks like this. What about our antiproton? Well, an antiproton is going to have a charge of -1, right? Because an antiproton has the opposite charge and also opposite spin. Turns out that antiparticles have opposite spin as well. So this is antimatter, not negative matter, but this is the kind of matter that if you combine it with positive regular matter that is in our universe, it is a complete conversion, 100% to energy. Okay? But we need to account for the antiparticles as well. So the antiproton then with a charge of -1, you could say, well, I could get -1 then with 3 down quarks. But no, that's not the way you do it. you do it in terms of the antiparticles of the proton. Okay, and so these have to be mixed up then so that it's in a 2-to-1 ratio. So you'd have an anti-up, an anti-up, and an anti-down. That's how you get an antiproton. And so the anti-up then has a charge of -2/3, and the anti-down has a charge of +1/3. Because remember, the down quark had a charge of -1/3. Okay, and so that gives you your net positive, your net negative charge. And similarly for the anti-neutron, you could say, well, since the neutron and the anti-neutron don't have any net charge, then I could just use the same quarks, and it must be its own antiparticle. No, not true. We have to use antiparticles, so we have an anti-up and 2 anti-downs. So we always want to remember that antimatter particles are made out of antimatter quarks, at least when we're talking about baryons, as is the case here. Okay, so we had 2 downs and an up for the neutron, and so the antineutron is an anti-up and 2 anti-downs. And so that still has a charge of 0, but it's made out of the appropriate antimatter quarks. Okay, and so the next thing that we might want to consider then is, well, how are these things held together? It looks like you've got a whole bunch of, here you've got negatives that would repel, and here you've got a little bit of positive that would attract. So it looks like the whole thing would fly apart electrostatically. Similarly here, you've got some positive, but you've got negatives. So the negatives could attract to the positive, but then the positives would tend to fly apart. And it turns out that electrostatic forces aren't how the quarks hold themselves together, but rather it's by means of color charge. So the mechanism of the binding of the quarks, which is a very strong aspect of the strong force. I've actually got, let me just state this here before we go farther. The strong force has 2 aspects to it. One aspect to it holds together the quarks. In a baryon, or also a meson. I haven't gotten to mesons yet, but the strong force also holds those together. But there's also a second aspect to the strong force that holds together the nucleus, the protons and neutrons in the nucleus. So one of them holds the nucleons themselves together, which, as I mentioned, were once considered to be elementary particles in their own right. But no, they're made out of quarks, and then maybe the quarks are made out of even smaller particles, but we're not going to assume that things like prequarks exist, although there have been some theories that have attempted to show that there is another layer, at least, of reality beneath the one that we're looking at here. So we've got these quarks being held together in a single particle like a neutron or a proton, and then we have the neutrons and the protons being bound to each other by another aspect of the strong force. So I'm going to go through each aspect, but I'm going to start with this one. Okay, so how do we bind together the quarks in a baryon? Well, they exchange virtual particles, and those virtual particles are called gluons. And so we'll start noticing here that some of these names are getting a little bit out there. that is part of the craziness that's associated with working with this stuff, is it just kind of, your mind starts to go, and then you come up with all of these strange names for these particles. Okay, so we saw before that exchange particles are responsible for all of the forces in nature. And so they are virtual particles that are exchanged between other particles. And so in the case of the, let's say, for example, the neutron or the proton, let's just go with the neutron and the proton and not the antiparticles for a moment. We have three different charges in the nucleus. And so that requires a little bit of explanation too. But why do we have three? Well, why are we so sure that two is the only kind of system that we could have? You know, we know that in electrostatic forces, you have two charges. And so we call them positive and negative, and they attract. But there was no guarantee with the electromagnetic force that you'd only have two types of charge. And this is not the case with the nuclear charge. There's three types of nuclear charges. And these are attractive charges. And because it is kind of the electrostatic force on steroids, we call it hypercharge. And so associated with the nucleus, then we've got red, green, and blue. Now, okay, so here's our green one. For our red one, I'll use this orange. Now, these colors are not meant to indicate that charges are color, but rather that we have a set of 3 different types of charges, and we can't just equate them to positive and negative, okay, because there's 3 of them. And so how else can we identify them as being separate from each other? And the answer is, well, we'll just make them the primary colors of light. Okay, because why? Because we know that red, green, and blue light adds together to produce white light, or no light at all, essentially. And so we could have the analogy here that equal amounts of red, green, and blue give us 0 hypercharge, just the same way as equal amounts of positive and negative give us 0 electric charge. Okay, and so without worrying about whether our quarks for the proton and the neutron are ups or downs, let's just look at them from the standpoint of their color hypercharge. So this one is what I'm calling the red one. This one is what I'm calling the blue one. Sorry, I don't have blue here. But that's the way it goes. And then this one here is the green one. Okay, so these can a red, green, or a blue can either be an up quark or a down quark. But we can see here that it's the attractiveness of the different kinds of color charge for each other that is responsible then for binding these quarks into a lepton. Okay, and so they're all attractive for each other, but they give rise to 0 total charge. Okay, so doesn't that kind of remind you of an atom that has a positive charge and a negative charge, and there's 0 total charge on the atom from a distance? Here, we're talking about a nucleon, specifically a baryon here. And so these things then are held together by this nuclear charge. So where do the gluons come in? Well, remember that our exchange particle for the electromagnetic force is a photon. So it's actually a photon that's being thrown. Think of it as being like a boomerang, if you want. Throw it like that, and it comes in and is received by the negative charge, and that creates an attractive force. Or you could imagine 2 positive charges exchanging particles directly, and this would be just like throwing something at someone, having them catch it. Then you would recoil, the person that catches the particle would recoil, and this would result in either an attractive or repulsive force. And so what kind of an interaction do we have here that's analogous to the exchange particle for the electromagnetic force? Here for the strong nuclear force, it's a gluon. Okay, so our gluon then is exchanged, and that gluon has to have just the right combination of colors and anticolors to make this work. Okay? And so this is a virtual gluon then. And it must contain a color and an anticolor. So in other words, you can have red, green, blue, but you can also have anti-red, anti-green, and anti-blue. Okay, so you've got three different kinds of color, but for each one of those you can have the corresponding anti-color as well. And so let's just imagine then that this kind of an interaction has to preserve a colorless nucleus. Okay, so that's one of the things that we have to have here is charge conservation. And so this is also hypercharge. So if this nuclear reaction doesn't conserve hypercharge, then that means that the total hypercharge of this, this baryon is not going to be zero after the interaction takes place. And so what we have to have then is a color and an anti-color in this virtual gluon. And so this is allowed by the uncertainty principle, that you can produce an exchange particle. And this exchange particle has mass. And so that means that it's only very short range. And this is why the nucleons can only hold themselves together over a very short distance, is that you have massive particles that have associated with them short range. And so the trick here then is that in exchanging this gluon, the result in the exchange of a gluon between a red and a blue quark is going to be an exchange in the color identities. So the red quark becomes a green quark, or the blue quark, and the blue quark has to become a red quark. Okay, so the exchange then of this virtual gluon then actually causes the color of each of these gluons to switch identity. So it's almost like they're switching places with each other, at least in terms of the color, when that virtual gluon is exchanged between them. And so let's see how this can come about in the first place. A red quark here. And so this gluon then is going to have to take away the red color. But by the uncertainty principle, what we're going to need to do here is produce a blue anti-blue quark pair. Okay? And so this is then produced because of the uncertainty principle. Produced by delta E delta T approximately equal to H bar. So in other words, this virtual gluon pair can be produced as long as the energy is equal to 2 times the mass times the speed of light squared. Okay? And then what we're going to do then is take this anti-blue and give it to the gluon. And that leaves behind the blue here. So in other words, the red has gone to here, and the anti-blue has gone to there, and so that leaves the net color of this quark as being blue. Now here on the other side, remember this was red. Here on this side, this one was blue. And so here we have a blue combining with an anti-blue because it's being delivered to this one. So we have blue anti-blue. So these cancel out, and we also have the red. Okay. So in the process then of a red quark being exchanged with a blue quark, we produced by the uncertainty principle a blue anti-blue quark pair. We sent the anti-blue along so that it could cancel out with the blue that was already in there, and so that leaves that quark as being red. But on this side, this was a red quark, and so that red and the anti-blue went into the gluon. So all that was left then for the red quark is the blue color. Okay, and so this process then of exchanging the gluon not only cements them together by means of this virtual particle exchange, but it also causes the gluon pair to exchange identities, so that the blue becomes a red, the red becomes a blue. Now what happens if we went from blue to green, this way? You might want to turn off the video right now and see if you could figure this one out. But if you want to just watch me do it, which isn't going to give you a lot of practice, but I'll do it right now. So here's our blue, here's our green, and now we're going to exchange a quark between blue and green. Okay, and so that quark then is going to have, well, it's taken the blue away. And we know that it's going to have to cancel out the green, so it's got to have an anti-green. That means in here we've got to have a green anti-green virtual pair that's produced by the uncertainty principle, so that we can send the anti-green along with the blue, and then what we end up with then on this side is just a green quark. And then on this side, the green and the anti-green cancel, and so what we end up with on this side is a blue quark. So we went from blue to green like this, but we did it with a blue anti-green, and now they've switched places. Now this one is green and that one's blue. You see how that works? And then we could do that one more time here. Should definitely turn this off now and see if you can do this one. And then see if you did it right, because I'm going to just keep going. Okay, so if we're going from green to blue, then we're going to have to send the green color away, and we're going to want to cancel out the blue, so this will be an anti-blue, right? So that'll make this quark a green quark, but by taking away, now here, what we're going to have to do, because of the uncertainty principle, is allow for the production of a blue anti-blue pair. Okay, so this again is caused by delta E delta T approximately equal to H bar. So under the appropriate field, you could also get red and anti-red, blue and anti-blue. But the only ones that are going to be possible reactions are the ones that conserve charge. Okay, and so that's why I'm picking out the ones that are relevant for this particular exchange, and not the other ones, which don't really matter because they're not allowed, because they wouldn't give the nucleon the kind of symmetry that this gives us. Okay, so what's left then, because this has blue left over, and anti-blues cancel out the blue here, so this has become green. So this is the result then down below. This one is green, and then this one, because the green has been sent away along with the anti-blue, is left as being a blue color. Okay, and you could do the other interactions too, in which the red is exchanging one with the green rather than the green sending one to the red, and you get a whole bunch of other possible interactions as well. But what this does is this allows for the conservation of hypercharge by ensuring that although the color identity of the individual nucleons has changed, the total color charge of the nucleon is 0. It's colorless because of the fact that we have equal amounts of red, green, and blue. And remember that adds up to 0 total hypercharge.